Good morning, this is lecture number 23, module 4 on matrix analysis of structures with axial elements. If you recall, we started this topic in the last session and we introduced the conventional stiffness method. We are going to continue with that method and show how it can be applied to analyzing axial systems and plane trusses. This is covered in the book on advanced structural analysis. So let's look at this problem once again. Do you recall this problem? We started with this problem. We are now going to do the same problem using the displacement transformation matrix TD instead of the TI matrix. Okay. Now please pay attention and work with me so that you get the hang of this. This is actually easier to do by this method because you don't have to worry about the linking coordinates. But you are dealing with larger matrices. Of course, for this problem it's not very difficult because you have only two elements, but in real life problems, big trusses, it's a little unwieldy, but it's good for manual analysis. So the procedure that we use when we use a TI matrix is shown here. I am just reproducing something that we saw in the last session. What is the change that we need to do? In which of these steps do you think a change is needed when we use TD instead of TI? In the first step, what kind of change is needed? Well, the transformation will look like this, right? D star is TD into D, that's for the assembled one. And if you are doing it element by element, it's di star is equal to TID into D, and for the forces you have the contragradient principle, which means you have to take the TD transpose. So if you are doing this method, then you forget about the TI matrix. This is the replacement. What about the fixed end forces? What's the correction we need to do? You've got the fixed end forces at the element level, the local coordinates. How do you switch to the structure coordinates? You have to pre-multiply with what? Not the TI transpose but with TD transpose. Okay, so that's the only other change. Everything else is the same. The second step, will there be any change in generating the stiffness matrix? Remember, in the earlier method you had to actually slot them with the linking global coordinates. You don't have that problem now, so it's simpler. This is the transformation you will do and you can sum up for all the matrices. We will demonstrate this. You end up with exactly the same structure stiffness matrix, so it's just a choice. For programming for large structures, TI is the traditional way of doing it, but for manual analysis or for smaller structures you can use TD. What about the third step? Will there be any change in this? No, third is identical because there is no TI, no TD coming into that. We are just solving equilibrium equations. So you solve the first equation, you find the unknown displacement dA, substitute it in the second equation, find the unknown reactions Fr, and then you find the member force. In the member forces, any change? There is a change because TI is not going to be used. So the change is TD. Now I want you to look at this carefully. In this last step, we actually calculate from the DI. The DI are those components of the displacement vector of the structure which are relevant for that ith element. So the size of DI will be how much for an axial system element? No, that's for a plane truss element. For an axial element, 1D element, it's 2 by 2, okay. But here you don't have to worry about selecting those values, you can directly deal with the D vector of the global structure. Okay, you will understand this as we work. So let's do this together. You have two elements. The global coordinates are 1, 2 and 3. There is only one active degree of freedom, that is number 1. 2 and 3 are restrained. We are just repeating the same problem we did in the last class, and the local coordinates are exactly the same as we did earlier. There is no change. I am just showing you this. What is the first thing we need to do? We need to write down the TD matrix. Can you write it down? How do you write down the TD matrix? Give it a try. You can write down separately for the two elements. Take the first element. What is the TD matrix? So for the first element, if you pull D1 equal to 1, what will be the reflection that you get in the first element? Okay, so let me help you with that. You need to write this matrix. It will actually look like this. It will actually look like this. Why do we say that? So take a look at this. This is your TD matrix. To fill the first column, and mind you there are two elements, this belongs to the first element, this belongs to the second element. When you, to fill up the first column, you apply D1 equal to 1, which means if I put a unit displacement here, what gets affected? Well, this gets affected and this gets affected because they both connect to the same point, right? Does this get affected? Because you are applying only a unit displacement one at a time. Does this get affected? No, that is arrested. Does this get affected? That gets, so it's simple logic. So it follows that D1 1 star is 0 because you do not get any displacement here. D1 2 star is 1, the same as the movement you get there. D2 1 star is 1 because it should match with D1 equal to 1, and D2 star is 0. Does this make sense? That is all. Now you apply D2 equal to 1, that means you are filling up the second column, but you are applying D1 equals 0, D3 equals 0. What do you end up with? If you put a unit displacement here, only this gets affected. There is only one, nothing else gets affected. All the others are 0. So does this make sense? Similarly, when you pull this third one, you will get this. Okay? So it's actually easy. You can generate it using first principles, but you can also program it because it will always be filled with ones and zeros. So you have got your TD matrix. Your next job, you have got TD1, TD2 put together in one box, is to get your fixed end forces. Now in this method we have done this calculation, remember? Can I assume that we accept that the fixed end forces as shown here? We did it in the last class, remember we had a long discussion. How do you convert it to the structure? How do you convert it from local axis to global axis? So this is the local axis, agreed? For the first element minus 20 minus 20, for the second element minus 20 minus 10 kilonewton. Do you understand? This refers to this element, this refers to this element, minus means pointing in towards the left. Does it make sense? We did this in the last class. Now you have to switch from here to the global axis. How do you do that? Actually you want to go straight to the structure. How do you do that? TD transpose. So you do that. You have already got TD. Will you work this out yourself? Tell me what the FF matrix will look like. There are two ways of doing it understanding every step, which means you need to follow the class. The other is just copy what is written on the screen. When you understand it, everything is clear. So I want you to raise questions if you are not getting it. This step is very simple. You have got the TD matrix, take the transpose of that and multiply that with this. Do you get this? That is it. We got the same vector using the TI formulation. This is the only difference. Is it clear? Which is easier, this one or the previous one? This one. I mean, because no thinking is required, you are just multiplying matrices. Got it? Let us proceed. What is the next step? We got the same answer. Next step, you write down your element stiffness matrices. This is just the same way we did last time. Can you generate the structure stiffness matrix by the TD formulation? What should you do next? Okay, this is, if you want to put it all together and have the unassembled matrix, you remember, you can, whatever you got here, K1 star you should put here, whatever you got here as K2 star goes here. Remember, it is a diagonal matrix, they are uncoupled. How do you use this matrix to generate your final answer?
It is.
Okay, you are not thinking. I want to generate the structure stiffness matrix K, and I want to do it in terms of this matrix K star, which is a diagonal matrix as shown there. That is all. So I do TD transpose. Now I want to raise an issue here. You need to do one of these multiplications first. Would you prefer to do this one first or this one first? A or B?
Sir, right side to first.
Right side you would like to do first. Why is that?
Because
we will be using it
like
in calculation.
Because this quantity will come in handy later in calculating the bar force.
Bar.
How does it happen? Well, if you look at the big picture, you have the structure, you have F star, you have F and you have D, and you've got F star and you've got D star. This transformation is given by what matrix? TD. This transformation is given by what matrix? What is this principle called?
Contra
gradient
principle.
What is this relationship? At the
K star.
K star. This is assembled, this is an unassembled matrix, so it is a diagonal matrix, right? Because it has got as many elements as there are in the structure will be put all in an uncoupled manner. What is this relationship?
K.
So remember this, and this basically is a mixture of FA, FR, and this is DA and DR, and similarly you can partition this K matrix into K. We will see that shortly. But at the end of the day you are going to find out this, and this is known, it is known to be 0. You want to find the internal forces, these are the member end forces. So you have a shortcut route here. After you know this, you can get this directly by doing this transformation. There you are, K star into TD, and then the next transformation K is given by this times this, TD transpose K star TD. So now you see why it makes sense to do this calculation first and store it in your computer, because you can pick that up later when you find the membrane forces. Is it clear? So you do it in 2 stages. First you calculate this, then you pre-multiply with that. You can do it in one shot, or you can do it in 2 steps, or as many steps as you need as there are members. So you can do it at the element level. Okay. For the ith element, this will be written as TD I transpose Ki star TD I, right? So you got K1, K2 in this particular problem. And what will be the size of this matrix for this particular problem? What's its size? Yeah, what's the size? It's 2 by 2. What's the size of this matrix? Well, it will look like this. You got a 2 by 2 there, you got a 2 by 2 here, and So you got 4 by 4, right. So you got 2 by 2 here. What's the size of TDI?
4 by 2. 4 by 2.
No.
2
What's the size of this? This includes all the elements. What's the size of this?
2 cross
That's the one we did.
2 cross 1, sir.
4 by 2.
2 cross 1. TID is 2 cross 1.
How many global coordinates are there?
3.
So what's the size of this vector?
3.
It's 3 by 1. Okay. What's the size of this one?
4.
Well, 4 by 1 if you're assembling them all together, right? So what will be the size of this?
4 by 3.
4 by 3, right? So remember, this is 4 by 3, but for each of them, what will this be? This is 2 by 3 because it's each element has, the element looks like this. It's got 1 star and 2 star. That's all it's got. You got element 1. Likewise, you got another element 2. That's how it works. Does it make sense? So what you do this, and you add up the contributions for the 2 elements with the summation sign. So there are 2 ways you can do this calculation. Let's see that. Okay. So you can do it this way and you will get the same answer that we got earlier, or you could do it, okay, I have not shown that step. You can do for each element and add up the contribution, you will get the same answer. Now what do? You do exactly what you did earlier, so I can go fast. You can find the unknown displacement, plug it back into the second equation and get your reactions. Then you get your member forces. This is where you can use the transformation. You get the same answers, so let's not spend time. You get this response which we got earlier. Okay, can we move on? So you have 2 options, either use the TI method, which is the conventional method, or use the TD method, or better still learn to use both the methods. When we study the reduced element stiffness method, you will use only TD, there is no TI. Second problem, take the same structure, okay, now there is no loading, no direct loading, and let us put some indirect loading. Let us put 2 kinds of loading. One, let us say there is a temperature change. So you have a temperature rise of 40 degrees Celsius in element AB and 20 degrees Celsius in element BD. What do you think will happen to those 2 members because of this rise in temperature? They will both go into compression because they are not allowed to expand. On top of that, let us throw in some support movements. So you got support slips to the right of 2 mm and 1 mm at A and D. The most complex problem is a combination of this and direct loading, but that you do for your assignment. We will do it slowly. How do you handle this problem? Okay. First, how do you write down the input data in a vector form? What is the input data? Well, you got temperatures, and you got the coefficient of thermal expansion. Okay, so you can write down your 2 temperatures, delta T1, delta T2, and you know dr. Dr is, we will choose the same coordinate system, agreed. D2 is 2 mm, which can be written as 0.002 meters, and D1 is 0.001 meters. Both are positive because they are pointing from left to right. Is it clear? This is the given data. How do we proceed? Actually, much of the work is already done because you have already generated your TI, TD, and you have already generated your element stiffness matrix. So it's, your load has changed, that's all that's happened. So you don't need to do any laborious work. Okay, so these are the steps. First, generate, I'm going to show both methods, TI or TD. If you are doing TI, write down the TI values first and generate the fixed end forces. How do you get the fixed end forces? Take any bar, lock its 2 ends, that is a primary structure, allow the temperature rise to happen, that bar will go into compression. The force in that bar is given by what? That is what we call delta NIF, that is a fixed end force in that bar. It will be minus because it is going to go into compression. the axial stiffness is EAI by Li, and E naught I is the thermal, that is L alpha delta T for the ith element. Is it clear? So this is known, and then do you agree that if this is going into force delta Ni, that force has to be equilibrated by equal and opposite forces at the two ends, right? So can I write it like this, on the left side plus delta NIF and on the right side minus delta NIF, that is my delta Fi star F, that is my fixed end force, clear? This will give me compression, I mean because Ni is turning out to be negative, is it clear? That is how you do it. So I can find out my fixed end forces, if I am, and I get my net load vector, that is Fa minus delta FFA. If you have this combined with intermediate loads, then you have to add that part also. If you are doing by the TD method, everything is same except you use TD and TD transpose. Then you generate the structure stiffness matrix, you do not have to do any extra work because we have already done this. You can do it either by the TI method or the TD method. Then you apply the basic equilibrium equations. Please note in these equations you have Fa Fr, in this problem Fa is 0 because no loads are given to you, and you have this fixed end force vector which we know how to derive. Substitute those values and you solve for dA, plug in the value of dAs and you get Fr. Yeah.
In that minus delta NIF and plus, no sir, minus and plus,
Yeah,
no
you
sir.
can write it either way, fine, you must get it right, okay, either you can write it this way or you can put minus.
In that if we keep minus in the first one delta n,
Yeah.
and here in delta F it is minus delta n and plus delta n, no sir, in that matrix.
In that vector, yes, tell me.
Minus delta n and plus delta n.
Let us look at it. This is, please listen, this is my vector. Let me not prejudge the issue, let me say this has some internal force delta Ni F. Can I say that? This is arrested due to some reason. Let us say I cool this bar, I reduce the temperature, then it goes into tension, you agree? So if I can show the tension like that, which means it must be equilibrated by a force like this and a force like that. So my fixed end force vector F for the ith element, this is the ith element, star F, what will it look like? It will look like minus delta n IF plus delta n, absolutely right. So this is my first principle. What do we have on the screen? We got plus and minus, so well caught, that should be flipped. So Ramesh, that is a very valid point. So if it is compression, it will show up in delta Ni inside, so please note this expression was correctly done, this should be minus and this should be plus, correct. Let us proceed. After this you find the member forces, you can do it by both methods, let us see how to demonstrate. So you have got global coordinates, you have got local coordinates, we do not waste time, this is the input data, you do not have a direct load vector, you have done these two calculations, either you do it by the TI method or you do by the TD method, both expressions we have. Now we calculate the bar elongations, there it is a rise in temperature, so E is positive. This step is straightforward, L alpha T, L is known, calculations are straightforward. What do you do next? You find the axial forces, they turn out to be compressive, is this step correct? Now is where we need to do it correctly. Now tell me if what we have done is right, is this correct? Is this correct?
Yes sir.
It is correct because minus
sir.
of minus turns out to be plus, and plus turns out to be negative. Finally, you must be sensitive to the answer. When you see an element like this, the axial force is given by this value, not by the other value, please note. So if this is moving this way, you have got tension, is it clear? So Ni in general is given by Fi 2 star, this sign will always match, clear? So here 2 star is minus, that means the axial force is negative, is this clear? So the first element has an internal force of 44 kilonewton, the second has 11 kilonewton, and both are compressive. This is before you started the analysis, that is, this is the kinematically determinate primary structure. Now what do? Now you release the active degree of freedom, right? So how do you do this transformation? Well, you have to move from element level to structure level, but so you do this transformation, you have these matrices, but you put the linking coordinates. Remember, the first element is linked with 2 and 1, the second element is linked with 1 and 3. So I think that this should be 1 and 3, right? And when you add it all together, you get 1, 2 and 3, is it clear? You can also do it intuitively, you will get the correct answer. Then you got the fixed end force vector, you have the K matrix. If you are doing the TD method, it is direct, no thinking, you got the TD transpose and you can directly get the answer, and then you use the same equations, you solve these equations. When you solve these equations, you can find the unknown displacements. Okay, please note, this is the equation, you got the stiffness matrix, F1 turns out to be, F1 is the load vector, Fa is 0, so there is no load here, you have only fixed end forces here, minus 3 plus 44 minus 11. So solve the first equation, find out d1, mind you, you have dr, okay, dr is non-zero, so you plug in the value, find d1, it turns out to be 6.7 mm, find fr, you get 20.5. What does this mean? Plus, is it compression or tension? Compression. So what is, it is very interesting, you had two elements, the two elements had different lengths, they had different cross sections. If you treated each one independently and you arrested the two ends and heated, you got different forces, you got 44 in one, you got 11 in the other, but they actually have to have the same force to satisfy equilibrium, and that force you can intuitively guess is between 11 and 44, it turns out to be 20.5, okay. So that is it, these are your reactions. After you get this, what is the next step? What is the next step? Well, you can also see how it has moved.
We can find the elongations.
D1 has moved 2 mm because that is given to you, D3 has moved 1 mm, it is given to you, and D1 has moved 6.7 mm. So you can draw roughly a shape to scale to get an idea of the numbers. Then you can find the bar forces either using the TI method or using the TD method, but you knew the answer anyway because you got the reactions, but might as well go through this exercise, you will get the same answers, okay. If you want, you can plot the variation of axial force, it is constant in both the elements, it is 20.5, and D1 has a displacement of 6.7 mm, D2 has 2 mm, D3 has 1 mm, it is a linear variation. Is this clear? This problem is straightforward. This is a problem, when I put an asterisk, it means it is a reading assignment, okay. This problem is solved in the book, you can give it a shot. What is the difference between this problem and the first problem? You have a free end at A, so your active coordinates increase to 2, so your degree of kinematic indeterminacy is 2. By the way, what is the degree of static indeterminacy?
Under
What is the degree of static indeterminacy? Give me a number.
Under is it?
Huh?
Under is
Okay, you are saying it is unstable, but we are doing structural analysis. Can you have equilibrium in unstable structures? Of course you can. Of course you can. So we are asking you to find the displacement and forces. Maybe you will be happy if I turn it over by 90 degrees and make it vertical, so you have the feeling the whole thing is going to come down due to its self weight. But in this problem it is a weightless bar, do not worry. So it is suspended in air and you can still apply this load. Is it clear? So do not worry about that. For this loading, do you have an answer? Do you have actual forces? Can you find them out? Sure you can. Okay. But it is statically determinate. So I do not want you to forget your basics. Can you quickly draw the axial force diagram? What will be the total reaction at D?
70
Tell me the number.
110.
110.
110 kilonewton, right? Show me how the axial force varies from A to D. Can you just draw it? Because that is the end answer you get from stiffness method. So you can predict the answer in advance. The degree of kinematic indeterminacy is 2, but the degree of static indeterminacy is 0, which means you can get the answer very easily. Will you draw the diagram? Draw the axial force diagram. You are supposed to be experts with statically determinate structures. Can you draw it? Okay, did you get this? Okay, good, wonderful. Now the next question is, in the stiffness method you will get displacements at A and B definitely, right? How do you get those displacements using the force method? With whatever little you have learnt, we did a review. How do you find the displacement? You apply unit load, principle of virtual work, right? Let us say I want the displacement at the free end at A, and what will be the axial force inside the system due to a unit load? Constant. So what is the formula for dA? For, yeah, so it is just the area of this diagram that we drew divided by EA. So it shouldn't take you much time, you can check it out. But you have 2 degrees of freedom. I am not going to solve the problem, I am giving you the answers, check it out, okay. The answers turn out to be 60, 64, just check it out. Okay, this will be your diagram. The problem that I have given you in the assignment is this one. Okay, this is the problem that you have got in the assignment. It is a little more complicated because now this is also statically determinate, so you can actually get the answers. The reaction is known. Here I have put one spring at the end. Will that complicate things? No, don't tell me it is unstable. It may be, but I am asking you to find the forces. But what do you think will be, what is a complication? Is there a complication? No, actually you have been dealing with springs all the way. The axial element is a spring element, or the spring element can be interpreted as an axial element. So you will treat it as a third element, that is all, third element. So choose these coordinates that I have indicated, 1, 2, 3 and the 4 is restrained, and do this exercise. This is a problem subjected to some intermediate loads. Can you solve this problem? So go through the steps, do it both by TD and TI, and you will be comfortable with this method of analysis. So I think simple 1 dimensional systems you know how to deal with. Can we move on to little more complicated problems? We will take trusses, okay. We will take a simple truss to begin with. If you had to do this problem, which method would you normally do? No, first what is the question? To find the bar forces, what method would you use? You will use a force method. Why? Because it is statically determinate, you know the answers, and you can also use the principle of virtual work, the unit load method, to get the displacement. But we do not want to do that method. we want to do it the hard way. We want to do the stiffness method, because did you know that the computer will only do by the stiffness method. Let us say you had a nice transmission line tower, spaced structure, it is mostly statically determinate, the indeterminacy is very low. So the standard software will choose to solve 120 equations simultaneously than do it by the force method, because you know that is how you program it, right. So this is a much smaller truss, very easy to do. How will you handle a problem of this kind? Okay, find the joint displacement, support reaction, then bar force. What is the first step? Well, okay, so you go through the procedure, find the coordinate transformations. Next, so once you write the road map, it is easy. What is the next step? The advantage of trusses is you do not get fixed end forces caused by direct actions, you will get them only caused by temperature changes or lack of fit. Okay, so you do not, so it is simpler. What is the next step? Yeah, you generate your stiffness matrices at this element level, at the structure level. What is your third step? Apply the same equation, so you will find that you are really, there is not much room for innovation here, you are just playing around with the same set of equations and find the bar forces. Is it clear? And you have the option of using either the TD or TI. Let us use the TI method and solve this problem. Okay, let us do it together. It is a simple problem, but the steps of it you should understand. You have 3 elements, you can name them 1, 2 and 3, and all the elements can have the same system of local coordinates. Here how many degrees of freedom you have? 4, because it is a 2-dimensional system. You have 4 degrees of freedom, we have discussed this earlier. Okay, let us start numbering the global coordinates. Where do you start? C, you are right, 1, 2, 3, those are my active coordinates. What is restraint? How many are restrained?
3.
3, simply supported. So 4, 5 and 6. You can choose any one, the sequence is not important. Is it clear? Usually after 3 you should put 4 near the 3, so I put it at B. Now what do? Write down your TD matrix. How would you do that? Can you tell me what is a TD matrix for a inclined truss element?
Cos.
There you are. So your loads are given in this problem. F1 is 30 kilonewton, F2 is minus 40. So you can do it systematically, handling as many members as you wish by writing down the element number, writing down the start node, writing the coordinates for the start node, choosing your some origin. Usually the extreme left lowermost location is treated as the origin. So you can write the, look at the notation that I put, start node XIS YIS for the start coordinate, XIE YIE for the end node. So your incidence is clear. Your length can be computed using this equation. So you know, I am doing it in a generalized way, you can do it for any truss, and you can work out the cos from the cos and sine from the direction cosine. Is this clear? So let us say I give you a bigger truss with 20 members. Let the computer generate all this, you just give it the table and it will do it in a minute, right. So you have got this, and using this you can generate your TD matrix. As you rightly said, this is how the TD matrix will look. Then what? Then you just generate it, that is all. So let us say the first element will look like this, because you have already got the cosine and sine values from the previous table, but now your job of putting the linking coordinates correctly starts. Okay, so you got this matrix by substituting cos theta and sine theta for the first element, but the first element is here and it is linked to 5, 6 at the start node and 1, 2 at the end node. So you have to put those linking global coordinates here. Is this clear? We have discussed this earlier, it is clear to you? Take the next one. Next one turns out to be like that. The linking coordinates are now for the second element. Well, it depends on which you chose as your start node. So let us go back. for the element 2 I could have chosen incidence from C to B, but in this case I chose from B to C. Do you understand? I do not have to break my head and calculate theta x. This will give me directly cos theta and sin theta from this formula. That is the beauty of this method. Is it clear? I get it automatically, I do not have any difficulty. So any questions here? It is clean. I do not have to manually calculate theta, it comes automatically when I give the coordinates x and y of the start node and end node. From these formulas, which are standard formulas, I get automatically the direction cosine. So it's a blind method, no thinking. The computer loves such method. Just all you need to write the algorithm, but don't forget your linking coordinates, and when you program it you must write down a subroutine which can handle this nicely. Is it clear? So that is why we got 3 4 1 2, and for the third element it start is here, the end is there, so it is 5 6 3 4. Is it clear? So can you generate these matrices? Very easy. What is your next step?
Big
Okay.
Element stiffness.
elements.
You generate the element and structure stiffness matrices. We have done this many times. The second row, the fourth row, the second column, fourth column will be 0. Why? Because they relate to shear forces which are 0, and there is no there is no independence between the first and third also, because one is the negative of the other. Okay, the rank of this matrix is 1. So you can generate this. All you need is the axial stiffness of the 3 elements. So EA is constant for all of them, only the length changes. For the first and second elements the length is 2.5 meters, and for the third element it is 3 meters. So 6000 divided by 2.5, so and 6000 divided by 3. Now what? Now you can generate K1 star and K2 star will be identical because they are symmetric and identical. K3 star will be different because the EA by L value is different. You got them. Now what do you do? Now you have to do the slotting business. So can you do it? Yes, we went through this exercise. You can do it. You first calculate Ki star Ti and put the linking coordinates and put the units also. It's all stiffnesses are kilonewton per meter. You can do this. You got Ti for every element, you got Ki star for every element. Can you not do the product? Can you not put the linking coordinates? What's the next step? You pre-multiply this with Ti transpose. You do that and you get this. Okay, you get this. From this, how do I generate my final answer? So what's the size of my structure stiffness matrix? 6 by 6, right? 3 active degrees of freedom, 3 restraint degrees of freedom. So let's just pull out KAA. How do I do that? So I'll show you stepwise. Look for where you have 1 and 1. So you got 1 and 1 coming here and 1 and 1 coming here, right? So pick up those values and add it up. So you have 1 and 1 here, 864 and 864 will add up to 1728. So can you do this picking up the slotting business? We discussed this earlier, and that is how you fill up that matrix. And likewise, sorry, yeah, this is what you do in the first step, this is what you do in the second. You can fill up all of them and then generate this matrix. Is it clear? Okay. Similarly, you can generate all the others, and it's a symmetric matrix, so you need to find only one off diagonal term, and you've got everything. Now forget this loading, you are ready to handle any loading on this structure, including support settlements and temperature rise or lack of fit. You are ready, and the moment you input the geometry of this truss, the computer will generate this matrix and say give me the load and I will give you the results. It is waiting. Okay. So how do you do that in this particular problem? You have no fixed end forces, right? dr is 0, there is no support settlement, so it is a straightforward calculation. You can find the inverse of your 3 by 3 Ka matrix, and mind you the units will be meter per kilonewton now because it is a flexibility once you have inverted it. Then multiplied by the load vector you will get the answers. Those are your 3 displacements. Then what? Once you found dA, what do you do next? Non internal forces come later, you need to get the support reaction from the second equation. See, you got 2 equations here. After you get this, apply that in the second equation, find Fr, and you know those answers because it's a simple answer, it's 40 and minus 30 because it's statically determinate. Then you find the bar forces. Okay, you can actually check out sigma fx equals 0, sigma fy at this stage, which you should as an engineer. Make sure equilibrium is satisfied, and then what? Find the bar forces. How do you find the bar forces? There are no fixed end forces, so okay, Ti transpose Ki. Here you have to be careful because from that large displacement vector, what is the size of the displacement vector? 6 by 1. You have to select only those 4 which pertain to the first element. So that is why I put a yellow color here to remind you that you have to do it carefully. So you take out those particular values 5, 6, 1, 2 from your dA dr and then plug that in, and lo and behold you get zeros, because for this particular problem for the loading you do not have any force in the first element. Okay, it is just an accident because the loading was such. Second element you get, so what do you conclude from the second solution? Is it tension or compression? It is compression because F3 star is the actual force, it is on the right side, and see your shear force is always 0, you could predict it in advance, and the other one is plus 30 kilonewton. So that is how you interpret the actual forces, and you are ready. Your complete response is shown here. You can draw your reactions, axial forces you can mark, even displacements you can mark, you know the joint displacements you have got, you know d1, d2, d3, draw it to some scale, and you can even sketch this, and if you are really interested you can also get the member bar elongations as EI is d3 star minus d1 star if you are really interested. You have got everything, you have got the complete force response and the complete displacement response for this loading. So can I assume that you have really understood, you can do the same thing with TD, just can I assume that you know conventional stiffness method? Okay, please do that example problem. Next class we will look at the reduced element stiffness. Thank you.